Hey everyone. Thanks for joining us for the next episode of our AI Apps and Agent Dev Days series with NVIDIA. My name's Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speakers for today. Thank you all so much for joining us.
Hello, everyone, and welcome. Thank you so much for joining. My name is Harmke Alkemade, and I work as a solution architect at NVIDIA. And today I'm joined by Diego, who works at Microsoft in the Global Black Belt team. And we will host this webinar on how to deploy the NVIDIA Agent IQ blueprint on AKS, on Azure Kubernetes Services. So for this session, we will have a short agenda. Let me show it to you. I will first start with a quick introduction on the NVIDIA AI Enterprise software and how to run it on Azure. And then I will hand it over to Diego to give a short introduction on the Azure Kubernetes Services platform and what you can do with that. But the most part of the session, we will be covering a demo on how to deploy the Agent IQ blueprint on Azure, and also how to run it in a way that it's suitable for production. So really focused on observability and interesting metrics that you can get from your deployment. So with that, let's get started. And I wanted to start with a quick overview on the partnership between NVIDIA and Microsoft. We actually have a very long-standing collaboration. It spans across 30 years already, and it has a lot of different components, as you see on the slide right now. So first here on the left column, you can see the NVIDIA accelerated libraries that are integrated in Microsoft Azure. So for example, NVIDIA NIMs, which is one of the components that we will be covering today, it can be used in Microsoft Azure to improve your throughput when running generative AI models. Or NVIDIA Rapids is another accelerated library that you can use to accelerate data science and data engineering workloads. So there are a lot of different libraries from NVIDIA that you can all run on Azure at scale. Next to that, we also have NVIDIA platforms which run on Microsoft Azure. So maybe you are familiar with NVIDIA Omniverse, which is a platform for creating digital twins and running simulations. It's available on the Azure Marketplace. Actually, if you go to the Azure Marketplace, you can search for NVIDIA and you can find a lot of these platforms and actually try to run them on Azure. We also have NVIDIA AI Enterprise available on Azure, which will be covered in the session today. So I will tell you a bit more about that. But also some more industry-specific platforms like BioNeMo, in case you're working with biomedical data and drug discovery and those sort of use cases. Next to that, what not everyone knows is also when you're using some of the native Microsoft services or tools, like Microsoft Teams, is that you're actually leveraging a lot of the NVIDIA libraries underneath to make sure that these tools can run at scale. So for example, if you're using the transcription capability in Microsoft Teams, then actually the model that is using for the speech synthesis is running on an NVIDIA library called Dynamo Triton. So as you can see, the collaboration is very broad and covers a lot of different perspectives. And there's also a big ecosystem around it with enterprises, startups, and ISVs. They are all leveraging these technologies on Azure to make sure that it runs at scale. And for today, we will be mainly focusing on agentic AI and how to deploy agents on Azure with NVIDIA software. So to cover some of the important innovations that NVIDIA did in this domain, I wanted to tell you about the Nemotron family of open source models. So these are generative AI models, which NVIDIA has developed internally and made available for the broader ecosystem to use. And with this, we are really focusing on openness. So these models are open source, open weights. You will find them on Hugging Face, but also a lot of the data sets that we have been using to train or fine-tune these models are available for people to replicate and to maybe customize them for their specific scenarios. So, and even based on all the learnings that we got from training these models at scale, we have a lot of libraries that are based on that. So for example, for fine-tuning or for the training process itself, we are also making sure that these are available for the ecosystem so that they can train or fine-tune their own generative AI models. And we make some of them available also in the form of cookbooks and recipes. So these recipes are really the training recipes that can be used to actually train these models from scratch, but maybe using your own data, maybe a modified version of some of the data sets that we have published, or the cookbooks which really show on how to optimally use these models when using them for inferencing in your own use cases. And lastly, to bring all these models together, because of course, when you're creating a Gen AI solution, it's often not just one single model, but it's a lot of different models together and being accompanied with other different services. So for that, we have the blueprints available, which work as an inspiration on end-to-end scenarios and how you can use these for your use cases. So, of course, the market of Gen AI models, it's very competitive at the moment. There are a lot of different open source models out there. But with a lot of them, developers have to make painful trade-offs between efficiency, openness, and intelligence. And with this Nemotron family of models, we are really focusing on creating the optimal version between all of these. And with efficiency, we mean like token cost, the latency, and the throughput that these models offer. With openness, we mean that, as I mentioned in the previous slide, that the models are available with open weights, that the data itself is public, so that a lot of different components that make up the eventual model are open. And we also focus on the intelligence, of course, to make sure that you actually get an accurate answer and that these models are suitable for complex reasoning. So with that, you will see that in a lot of public leaderboards, if you look them up online, you can see that the Nemotron models are included in that, with Nemotron 3 as the most recent model that we have published. And some of the interesting breakthroughs that we have seen by developing and publishing this most recent model, which is a Nemotron 3. It actually comes in different sizes, and the Nemotron 3 Nano is currently available. Some of the bigger ones will still be published soon. But the first one is on the architecture side. So we have Nemotron models with different model architectures, like transformer-based, like Mamba architecture. But the Nemotron 3 model is a hybrid mixture of experts model. And we are reusing the KV cache as much as we can so that we can actually, in a very efficient way, reuse the answers and the queries from users that have already been given. We've also seen a big jump in the intelligence when using some of the reinforcement learning techniques that we have implemented for this model. And they are also available for the ecosystem to use. It's the NeMo RL Gym. It's an interesting library to look at if you're interested in the area of reinforcement learning. And lastly, what is also interesting about this model is that it has a very long token length. So actually up to 1 million tokens is supported. So with that, you can process a whole book or a massive code base and still get a relevant answer based on your query. So as I said, these models are available open source, so you can go to Hugging Face, download these models, try them out. But what we also do is trying to make it easier for the ecosystem to bring these models into production by pre-packaging them in containers that can be deployed very easily in different container platforms. So we are calling these containers NIMs, which stands for NVIDIA Optimized Inference Microservices. And we are really trying to make it easier with these microservices for developers to adopt these models in their use case. So they are platform agnostic. They can be deployed on different type of container platforms. They also support the standard OpenAI chat completion format, which makes it easier if you have been using different models before or want to switch between different models. And they also support customization. So if you're working with fine-tuning, maybe creating LoRa adapters on your model, for example, then you can still use these NIMs, deploy them as containers, but then with your LoRa weights attached to them. So with the NIMs, we are really trying to focus on ease of use for developers. So these models become like a building block in your application. So in this slide, you can see an example of an agentic application where the agent has access to different skills and capabilities. And you can see that the model is just one of the building blocks that we associate with this agent solution. And of course, the optimal way for a developer to be working is that just by changing the model name, you can go from one model endpoint to another. So this is really what we're trying to achieve with these NIMs, to make it as easy as possible for developers to go from model A to B and to try them out and to see what works best for your use case. Because in reality, what we see is that it's not always so easy from an open source model to take it into production in a reliable and scalable way, because this means implementing an API, making sure that all the logic is implemented, but also focusing on the security patching, doing the load test, running it at scale, etc. So this can really take at least 5 days, for example, to make sure that a new model is ready to be used in an application. And with these NIMs, we're trying to reduce these 5 days to 5 minutes. So you really deploy a NIM container in a few simple steps. You have the endpoint up and running, and you can immediately invoke your new endpoint and use it in your code. So we have a lot of different NIMs. So I already mentioned the example of Nemotron models. So these are the models that we are developing internally. But we also have a lot of the open source models, like the Llama models, for example, that we have packaged as NIMs. And also a bit more specific models outside of the LLM domain, like computer vision models or speech models, or more industry specific like biology or simulation. So a lot of different options out there. And I can recommend, if you're interested, to go to build.nvidia.com. You will see the models out there and just test them out and explore the different options that we have. So the overall software suite, NVIDIA AI Enterprise, it's all available on the Azure Marketplace. You can use it actually in different ways. So of course, we have underneath the infrastructure layer with the different NVIDIA hardware components and GPUs. And on top of that, we have the NIMs available, and you can run them on, for example, Microsoft Foundry. We have some models, some NIMs integrated directly in Microsoft Foundry, but you can also run them on AKS. We will actually discuss both options today, or on a virtual machine. So it really depends on what works for you. So outside of the NIMs, we also have a software suite, which is called NVIDIA NeMo. And NeMo becomes relevant when you want to start creating a continuous feedback loop around your application, to make sure that you evaluate your GenAI applications, that you maybe fine-tune, do data curation based on the data that you're gathering from it. So this is like a set of SDKs and APIs and also microservices that you can use for that purpose. And on top of that, of course, to connect it all together, we have the NVIDIA AI blueprints, which are end-to-end use cases, which are made up of several of these components of the NeMo tools, the NIMs, etc., to make sure that you can easily get started with your use cases. So today we will also be discussing one of these blueprints. So let's go a little bit deeper on what it actually means. So these blueprints, you can also find them on build.nvidia.com if you want to explore the different options. But what is there inside? These blueprints have reference code, sample data, architectures. So basically all the different components that you would need as a developer to get started with your use case. Just to make it clear, it's not yet a production-ready end application. It would often require some customization to make sure that it works for your specific business scenario, but it still has a lot of the basics in place to help you get started quickly and to build your agents. So just some examples of the different blueprints. So today we will explore the Agent IQ blueprint, which is a research agent. But next to that, what we also have available is a blueprint for RAG, for multi-model RAG actually. We have some blueprints in the medical domain, so for example, for drug discovery. And also one which is very popular is the video search and summarization blueprint, which can be used to process videos and analyze the information that you find. So for example, in security scenarios or industrial domains, this is one which is being highly used. Okay, so let's move over to the Agent IQ blueprint specifically. So what is a deep researcher? So I assume that most of you are familiar with RAG use cases, RAG solutions, where the user asks for a query, and then based on a often vector database, relevant information is being processed, being summarized, and the answer is sent back to the user. So this works great for maybe simpler questions and when the user expects an answer right away. But a deep researcher really takes it one step further and makes sure to create a plan first based on a query from a user. So this can be a very complicated query, for example, to create a research article. Then it will still have a RAG component, so it can search through multiple sources to get relevant information. It will then analyze and synthesize the information that it found, and eventually it can create a research report with citations. So it can be used in areas like sciences, but also in business scenarios, financial analysis. So there are a lot of different applications for these type of agents. So the Agent IQ blueprint, yeah, it's really an example application that we have created for this purpose. And let's have a quick look at the overall architecture that we have for that. So here on the lower side, you can see that we have a full RAG component in this architecture for the Agent IQ blueprint. So actually, you will also see and hear when Diego starts talking about the deployment, that actually deploying the RAG blueprint is part of deploying Agent IQ. So this part has all the typical steps of processing business-specific documents, extracting the information, embedding them in vectors so they can be stored in a vector database. And as soon as a user asks a query, then this query will also be embedded and the most relevant documents will be retrieved from this vector database. And in this case, we also have a re-ranking model in between to make sure that, yeah, based on the documents that we retrieve, we can still sort it a little bit more based on the actual relevance. So that's about the RAG component here. Another data source that we can use is a web search. So in case we want to get additional information, or maybe not the information that we are asking for is not in our vector database, then we are using a Tavily service for getting information directly from the web. And here on top of this architecture is the agentic component. So for this, we are using the NIM Llama Nemotron Super 49B, which is one of the NIMs. Actually, all the green icons that you see here on the architecture are different NIMs that we have deployed. And this model is responsible for creating the plan, reflecting on the plan, refining. So this iterative process, which is needed to make sure that we can really answer these complex user queries that we're interested in with a deep researcher. Okay, so with that, I quickly want to show you also the end result of this blueprint. So let me switch over to my web browser. Because actually the Agent IQ blueprint, it comes with a UI, which you can use. And this UI, yeah, I just want to show you so that you actually know what we are building when we're going to the deployment steps later. Okay, so the UI is here and we can start conducting some research. We are selecting our reasoning model. In this case, we just have one, which is the Llama Nemotron Super model. And let's begin researching. So here we can actually start this process by selecting our data set. So you can also, of course, upload the custom data set. All of this is just to work as a base for your own use case. Of course, for any specific scenario, you would start with your own data. But just as an example here, we have ingested a small data set of biomedical data. And these are scientific journals, specifically in the area of cystic fibrosis. 44 PDFs, and they are embedded in our vector database. And in this case, what we say to the model is that it's a medical researcher specializing in cystic fibrosis, and we are asking it to create a specific research paper based on the research papers that we have in our database. We also give some information about the format, so what are we expecting in the abstract, the method, etc. And we are asking it to come up with cited resources to make sure that it's actually based on hard data. So in the next step, we can also select that we're interested to get some information from the web. So we can retrieve additional information if needed. And then that's all we need to start generating. And this is where you will see that it's actually a multi-step process, because where with a normal RAG agent, you would ask a question and get an answer immediately. In this case, the model will actually start creating a plan. It will create a plan and not immediately execute the plan. So that's what you see here. The first part is the reasoning steps. And if we click on it and expand, then we see what the model is thinking. Maybe this is not relevant for all users, but in this case, we can decide to show it because we're actually interested to know what is going on inside the model. So in these steps, it will just analyze the user query. And once it's done with that and it has a good vision of what the user is trying to achieve, then it will formulate a plan. So this is the plan of, okay, which sort of data do we need to retrieve? How are we drafting the report, etc. And if we want to, we can ask for specific changes. So even this process of coming up with a plan is iterative, so that we make sure that only the agent starts to invest time in a plan that we're actually happy with. So in this case, the plan is all good. We are happy with what it came up with. And then, of course, we should execute the plan. And this step can take some time, because this is a step where the agents will execute the plan and will go through different steps that are needed to eventually come up with the final research paper that we've asked for. So it starts with the RAG answer. So this is a step in the process where the model will retrieve the information from the vector database. So it will actually check, is there relevant information on this user query in our database? Which documents should I retrieve? There's a relevancy checker to make sure that, this data is actually relevant. And in this case, the web answer would say that the web search is not needed because we already found relevant research papers in our documents. And this is where you will see it will go through the different steps to eventually create the report. And as this will take some time, I already executed these steps beforehand, and we can go to the final report here. Yes. So here, again, on the left side, we can see the same steps, right? So the RAG, the relevancy, web answer, summarizing, and eventually it will create a final report and a finalized summary. And after that step is executed, you would see the report here on the right side. So it actually came up with a research paper on cystic fibrosis with the specific asks that we gave to the model in the format that we asked for. So it has an abstract and the methods, and it's actually a very extensive research paper, as you can see. And we can even continue here editing the report or asking additional questions. So in case that we're interested in getting the key points from this article or have other questions about it, then we can just ask for it. And if we're happy with the report, then we can download it. So that's a very quick overview on the Agent IQ blueprint. I hope this gives you a good insight in what we're trying to build here. And with that, I would like to hand it over to Diego to show you more on the deployment and how to do the observability for this blueprint.
Sounds good. Thank you, Harmke. I feel like I always learn something from you. I was actually taking some notes on my notebook here. This is excellent. So I appreciate that. And I'm pretty sure I'm going to come back with some questions once I start demoing this here. Folks, thank you for joining us. I am Diego Casari from the Migrate and Modernize Global Black Belt team. I'm coming today from Calgary, Canada. I did see a lot of people chiming in on the chat there. That's awesome. Let's get going with some of this stuff in here. I do like the idea of having this deep research capability that we're showing here today, running on Kubernetes, and that's really what it is running behind the scenes here. So we saw all of the context and the background information and how the solution is put together by Harmke, including I took some notes in here, plan, the RAG portion, the report with citations. And then now what you're going to come with me here is just see how things are done behind the scenes. To start, Kubernetes really is an excellent choice here, if not a prevailing solution for AI and modern apps. Now, when we're looking into that, there's a few things, and we do have a set of principles already applied on Kubernetes. And for us here at Microsoft, we're talking about Azure Kubernetes Service. There's a ton of capability built in. We ourselves use it. We're with our partners, NVIDIA here. We're doing a ton of this live whenever you're doing a Teams call and other things. And we're trying to make this as easy as possible. And that will probably be something you hopefully will take away from this presentation here today. I'll go back one slide real quick here. There you go. So who runs, AKS? Well, we run ourselves. Like Microsoft actually runs AKS at a scale. I'm putting out some of the context in here from ChatGPT to Office, Xbox, Teams, and of course, whenever you're using GitHub, we got Copilot, Claude, and all that good stuff that we're doing inside of VS Code. We're using AKS somewhere along the path there. So when we see that, and there is telemetry coming from AKS itself, our engineering teams will take that information and then reiterate over and over again and say, okay, what areas can we improve? What have we learned from running these ourselves? Which is great. And then it comes into the next idea here, which is, I really believe AKS is very well suited as a solution here for AI workloads. And what do I mean by that? There are a few things. One, today, you can actually run a lot of the workloads I'm going to be showing you on AKS Automatic. AKS Automatic is an option that we have where pretty much everything that we learn from our own experience and working with customers, from a best practice, ready to go, production ready type of environment is there. Safeguards are in place, best practices are in place. You don't really have to choose your CNI or whether or not you should be using a specific size for a VM SKU for your system node pools. We take care of that for you. It's enabled by default. So I do think that AKS Automatic is an excellent choice when you're coming to this new world we're living in now with AI workloads. So from a day two operation perspective, this will immensely help. Now, another thing that I want to mention here is that AKS today does support NVIDIA GPUs, and it's to be honest, I do feel like it's a game changer. It is seamless. You can bring your SKU and we'll detect and install the drivers for you. On the workshop here, I took a different path where I'm actually showing you all of the steps you need, because some SKUs might not have this built into them. But most of the time, for the majority of the SKUs, you don't need that. So what you're seeing with us here today is a full end-to-end deployment of the blueprints, the RAG and the IQ. But know that potentially when you're doing this on your own systems, you might not actually have a need to install like a GPU operator and some other pieces. So we do have that as an option today. Also, we make it enable a few things here. One is we do have the node problem detector, or NPD. When that's enabled for a few SKUs here with the A100s or H100s, and I do have H100s today, we will detect things like fault driver issues, flapping on the NV link or degradation from an InfiniBand perspective. So you do get that out of the box. Telemetry then will flow from whatever we detected in the card up to, with Prometheus, up to Grafana. So you can actually have that plotted for you and then, taking the appropriate measures after that. So this is a pretty interesting thing that comes out of the box as well. Next, on observability again, let's talk about what we can do, out of possible. So what you're seeing right now, it's a screenshot of something that I will show you live. So this is running on Azure, on AKS, and this is actually Azure Managed Grafana. All the telemetry will flow from a cluster back with Prometheus through Grafana, and then we can display that. You will see that in a second here. And then Lastly, here before our demo is the Azure Monitor Managed Service for Prometheus, which can, and I am actually using on this demo, will also make your life easier. At the end of the day, what we're looking for is how can we expedite a day-to operation experience for our customers? Again, based on things that we ourselves learn and then looking at customers. With this, you can do a few things. One, we're looking at, let's say, an application metrics that can be displayed under the slash metrics, like that is an HTTP endpoint, and we're gonna put those metrics out. If that's the case, then it turns out that we can just harvest those with Prometheus and then ship it over and have it display on Grafana. So it is demo time. It is our favorite time of the day. And then I hope the demo gods are on my side here today. I'll show you a couple of things. Let's start this backwards. I want to show you what the final result of the demo will look like. I'll make this layer full screen for you. There. Okay, so what do we have here? And we're going to get here. I will walk you through the process of getting here. For one, what you're seeing against is Azure Managed Grafana with a ton of telemetry. I'm going to just break this down real quick so we can have a logical concept of what I'm going to show you. And I'll come back to this. But just for now, we do have telemetry from the LLM itself, so from the Nemotron 49B. And these are the telemetry you see right in here, including, for instance, how many tokens were successfully processed, if we have any choke points, what is the latency between the end-to-end requests, interlatency as well, and we can plot that in heat maps or have that into different sorts of graphs. After that, we have visibility into the vector database, the hardware, and then some of the DCGM from NVIDIA, which is, again, hardware-specific information from the GPU. So let's come back to this, but this is where, at the end of the day, we're going to get into here. Now, looking over what we have, and Harky was explaining that, today, this whole solution can be deployed in 3 ways. Right? And then I'll share this link here. I don't know, Anna, if you mind dropping that link on for everybody. But what we have today is this. We have a way to deploy the model itself, so the NIM Llama Nemotron Super 49B on AI Foundry. That's one option. If you don't want to do that, you can also point that, at least from a testing perspective and learning, you just point that to build.nvidia.com, you got an API, and off you go. The third option, or option C for this, is to actually bring Nemotron, so the NIM LLM, into the AKS cluster. And that's what we have. That's what I'm going to show you today. So with that, let me walk through how this is done. Now, there's a reason why, I'm just going to scroll here to the first areas that we need. There's a reason why I'm not doing this live. We don't have time for the whole process, but I will walk you through what needs to be done, and then I'll show you the cluster, and I'll show you how this is actually fully configured. For my cluster right now, we have a few things. One, we have a standard D32S V5. This is all in the GitHub repo, so don't worry too much about the details about what size do I need there. But we do have 2 of them from a system node pool perspective. Then the core part of this, which is probably the part you're asking yourself, is, okay, he mentioned H100s. What are we talking about? For my demo, I'm using a standard NC80 ADIS H100 V5, so version 5 of that. You potentially will have to change this into something else. So an H100 is required, or an A100, but the SKU, the exact SKU might change by the region you're trying to deploy this on. But this right now will take 4 nodes of the H100s and then 2 nodes of the standard D series. Once we have that, everything here that I'm going to show you, and I'll show you here in a second, can be done through Cloud Shell. You do not have to have all of the tools needed, like Helm, kubectl, on your machine. If you do, great. This is just going to work the same way. You can also just go to Cloud Shell. And I'll show you that. But in the process here of deploying it, we'll show you where you need to go. So you go to Cloud Shell and then open a Cloud Shell tab on there. So I'll show you that right now. And I will move this and I'll bring it back here in a second. So if you haven't done this before, and I'll close this here so you can see it, this is how it looks like from an AKS perspective. Once you go to the portal, that's our cluster. You can see here that I do have the 2 node pools in it. So GPU pool and then node pool 1, one with 4 nodes and the other one with the 2 nodes, right? This one, the GPU one is the one with the H100s. From a Cloud Shell perspective, there's a little icon up here. You click on it. Okay, so I'm going to try to do everything from Cloud Shell. Again, you can 100% just do this from your machine directly. If you can, go with that. But if not, this is a way you can do it too. A couple of things in here. Let's just check that the cluster is up and running, which we know it is, but I'll show you that too. So if I just do a kubectl get nodes, we can see the nodes are in there, right? And then I'll do a kubectl get namespace. Well, so here's what the demo gods have for me today. Normally, between friends, I would have this as an alias on my machine. And we're going to do that right now on the fly. So alias is k equals to kubectl, because really nobody wants to be typing kubectl 1,000 times a day. So let's just go again. And let's see if I did it right. There you go. And then now we want the namespaces. So I do have a few namespaces in here. Let me walk you through them. The first one that I want to call up your attention here is the GPU operator. I'll show you how that gets deployed, followed by the 2 blueprints, reg, and then IRA or AI RA. We do have a ton of things running there. Let's just do a quick peek on what's in them, and then we'll go back to the instructions here in a second. So if we're doing a get pods on the, well, let's start with the GPU operator, because the first one I mentioned here. Here we can see that the daemon sets for the NVIDIA drivers are in place, among a few other things like the node feature discovery, the toolkit, the validator, and the DCGM explorer. And that's important because the reason why I have telemetry from the hardware itself, it's coming from the DCGM explorer. So that's on that namespace. How about if we just take a quick look here at reg? And that's what we have on reg, which includes things like the Milvus data store. So it's in there, and we're also retrieving metrics out of it. Should also look at the fact that we have the NIM LLM in place as well. And then the last one here, where we have the AIQ LLM running. So everything is in place, everything is running at this point. And I'll show you real quick, when you do the workshop on your own, what do we have to do? So first thing here, we're cloning the repo, which is probably the easiest way. You don't have to if you don't want to. I'll show you another path for that. But right now, what I want you to look into is this right here. So we're going to do a git clone. As it stands right now, this is on my own, GitHub repo, but we're moving that with a PR to the NVIDIA one. Once you clone that, we're going to go into NIM deploy. And then in here, you have the cloud service provider, Azure, workshops, and then AIQ. Now, you don't have to remember this. This is all in the workshop instructions itself, right? So if we go back in here and we scroll down, that's the first step we do. We go in Cloud Shell. Okay, so we're over that right now. And then we're cloning it. That's kind of what we're doing right now. And then we're doing a CD directly into the workshop directory. So that's a path you can do. If you don't want to do that, I do have all of the manifests that we're going to be using in a directory called manifest. So you can just use that too, if you don't want to clone it. The things you need for this, you do need an NVIDIA API key. That's core for the deployment. And then, of course, you also need Tavily. Harmke was showing that whenever you do a query or you're asking questions and then we don't have enough information from a RAG perspective, then we can enrich that through Tavily. So you do need that. Unless you don't plan to use it, then you have to uncheck that box. But all in all, and it's free, you just go in and get the API key. We'll need to use it. Of course, that by now, you do know that we're using Grafana and Prometheus. You will need those too. So I have that as instruction in here. Once a resource group is created and an Azure Monitor account is created, and then we retrieve the workspace ID, I'm going to plug everything in for you, right? Before the cluster gets created, we have a few things. One, once the cluster is online, I'm enabling all sorts of telemetry from a cluster perspective. Then I'm plugging in that with the metrics we have available. Moving forward, GPU node pool will get installed, which you probably already expect, but there's a caveat to this, which I already mentioned, that some SKUs will be automatically provisioned with the GPU operator. That's not the case here because I have very specific needs. So instead of, having it deployed and tweaking it, I decided to follow a different path, which we have in the MS Learn docs, and just don't install the driver. With that, we're installing the drivers ourselves. Few things to keep in mind here. We are enabling the GPU operator because we need DCGM as well. We're also enabling the toolkit for the collection of metrics, and I am not enabling a service monitor. So if you've used this before with Prometheus, you can collect telemetry from two things here. One, you can do a pod monitor where we're harvesting telemetry from a pod that can then be sent it over with Prometheus and plotted with Grafana. We're not doing that. And the reason for that is that I have to do some small tweaks just for this to work with manage Grafana in Azure. Again, this is all available in the manifest files. It's not, everything is in the manifest files, and I'll go there at the end here. I'll show you what's being done. Again, we went through this. Once everything is deployed, then I want your attention for two things. One, the RAG blueprint is being deployed too. And then for that, there are a value files that I call RAG values. It's in the manifest on this repo. We essentially deploy everything for you. I'm taking a couple of things into consideration here. If you were using this for a production environment, chances are you're following as the best practice of having tenets and tolerations about not scheduling non-GPU workloads on this H100 SKUs. That's in there. I've added for you. You don't necessarily need this for the workshop, but it's there in case you need a reference. It's already there in the Helm charts. All the both values for the RAG and AIQ will have that. Again, it takes a bit of time for everything to spin up. This is kind of why I'm just going through the flow here. Once that's done, you do have access to everything at this point. From a RAG perspective, you're off to the races, right? You can access the front end, you can load documents, you can create collections. Once you verify that that's done, it will come back into a choose your adventure sort of crossroads. Again, option A is Foundry, right? There are pros and cons about everything here. You need to understand what is that you're trying to do. Foundry, you can probably just use it. It's production workloads. It all scales. Like, just go with it. And it's done in minutes. You can do the build API from NVIDIA. We're talking about quick prototyping, testing, I think getting familiarized with different models. Excellent choice there. You don't want to have to wait minutes. You can just, seconds, you're off to the race. The third option is the option I'm showing you here. Again, self-hosting everything on AKS. This gives you full control, including having telemetry from the LLM, which I kind of think it's very interesting. So whenever I'm talking or doing the research, what is actually happening behind the scenes, right? So we have the ability to see that. In every one of this, if you click, you would see that would expand. and it will tell you exactly the steps that needs to be taken there. I'm going to move a little bit from here, and this is what we already showed you in terms of, hey, here's how it works. By the way, the files that you need for the collections, we also provide that. So NVIDIA made it this load files.yaml that really loads the two collections, the biomedical and the financial collections with all the PDFs, and you just need to run that against your cluster. So, and that's what you see, like that's what Harmke was showing. Now, once we move from here, right, let's talk about monitoring and observability, which is the first UI I showed you on Grafana. What do we have now? Because we have the NIM LLM in cluster, and we have enabled the DCGM exporter for the telemetry coming from the H100s themselves, we now have a multitude of telemetry. In here, I really only show you a handful of each one of them, and then we also give you that whole dashboard. It's on this GitHub repo as well, so you can just pull that in. Let me walk you through a couple of things in here, and I'll show you a few things. Oh, by the way, there's also something here that I won't have time to show it today, but it is Phoenix. So you can do some distributed tracing with Phoenix, and it is enabled by default on this cluster as well. So if this is your jam, go for it. It's there. It will actually be the next tool here in terms of, hey, how things are working? Because one thing is to see from a Grafana perspective, to have an overview of, hey, here's how my application is behaving end-to-end with latency, tokens per second, choke points. This gives you the next level in terms of what you can actually do and troubleshoot. All right, so going down here and coming back to this, let's see what we have. And you can see right now I'm getting telemetry for every 15 minutes. We can, of course, extend this back if we want. And when we're looking at this Nemotron LLM metrics, we can actually grab those, and I'll show you how from a different perspective. Again, this here is made available. It's free. You can just get it from the repo. What else do we have available, right? I've documented a few of them in here. And there is also a way, if you just want to kick the tires and see some of the telemetry being displayed and make sure that everything is actually wired up correctly, you can run a rag sweep job or a rag sweep benchmark. That's actually coming from a blog that NVIDIA wrote, and I'll come back to that at the end of the presentation, where they show how to auto-scale NIM. Now that you actually have the LLM in cluster and you have all of this telemetry, well, it turns out you can just use a horizontal pod autoscaler to scale things in and out. More on that later, but keep that in mind that you can actually run this. It's sort of like a performance testing just to see what's happening. And this will actually also validate whether or not all of your telemetry is in place, your service monitors are working correctly, your Grafana dashboards are collecting the right information. A few things in here. These are just the ones that I've picked based on the dashboards. And you can see from a Nemotron perspective, we have a ton of new telemetry in there. Again, including time spent processing input tokens, GPU consumption, average time between consecutive tokens, and things like that. That kind of information, including also queuing, will help you scale out these microservices, right? And this is a sample of what I was just showing you, but live. Same thing would apply for the rest here. Milvus will have its own sort of set of telemetry. The GPU coming from DCGM. And then there's an extra set of telemetry here. That's what you're seeing at the end. Also from this DCGM. So let's go back here real quick. What do we see here right now? Right, you see GPU, you see the Tensor Core. This will, of course, get generated every time a user is using the system that we have. The way you can actually retrieve some of this, and I'll go into a couple of them, is by looking at what telemetry that specific NIM is putting out. right? Let's look at the NIM LLM here for a second. So if we do, again, if I'm just going to go back to a kubectl PO, so we're looking at the pods on the AIQ namespace. And then I want to see if this AIQ NIM LLM here, what kind of telemetry we get, right? The typical approach would be this. You can, if you know by heart, that's easy. You would just know the port number. But let's suppose we don't, because a lot of this, because we have a lot of different components in here, might not all be publishing this telemetry to the same port number. So I'll show you how I typically go about that. So we're copying this out here, copy, paste that, and then of course that namespace. And we're looking at, I'm just going to expand this real quick. We're looking at some endpoints. Now, for this here, what I want you to take a look into is the port 8000, where it says HTTP OpenAI. That's the one. Now, the next step here is to do and remind you that K stands for kubectl. We don't have to be typing kubectl all of the time, all day long here. So port forward, and then the namespace is this one, AIRA. And who are we trying to port forward this to, right? So it is this guy here, and then the port which we just retrieved from up here, which says HTTP OpenAI, right? On port 8000. So 1, 2, 3. And it does say forwarding. Now, recall that I'm actually in Cloud Shell. How am I actually going to see that? That is a cool little thing here called Web Preview. 3. We're going to put plugin 8000 and then open and browse. And it's like, oh, we don't have anything in there. What is going on here? Well, let's see if we can do, because normally this would display under v1/metrics. So now you're actually seeing the raw metrics, right? Which is cool about this is that you would have 3 things. 1, a help, and I'll see if I can make this a little bit larger because I suppose that's better. You see help, so the help will tell you exactly like what is it that we're collecting with this metric here. Then a type, which is like a counter, right? The total number of tokens, and then there is a number. At the end of the day, that information, once we have it, we can then use it up here, right? With the total number of tokens, for instance. And you can see there's a few others here, including the end-to-end request latency and others. Now, if you come into a different model that potentially have a different set of telemetry, which is expected, it will likely happen to you. Here is how you can proceed. So taking this as an example, let me show you the other behind the scenes here, which is the manifest file. Specifically for the one that I just showed you, if you go into the repo and under manifest, we got everything in there. For a service monitor to work, right? And that one in specific, you can see that the name is in here, the namespace, which I'm filtering on. And then I'm looking specifically at a port. Recall that I had port 8000, but also I had HTTP-OpenAI that will work either way here. And then v1/v1/metrics. We're scraping that out every 30 seconds, and that is a timeout of 10 seconds. Same apply for everything else. You can see the Milvus vector store also has something, but it's under metrics, /metrics, not under /v1/metrics. Others are the same, other metrics as well, right? And then if we go down into the DCGM, those are specific from a GPU perspective and hardware information, again, like clock, frequency, bandwidth, and things like that, that the DCGM exporter gives you. They will be published under /metrics. I did mention earlier that, hey, I did not install this right out of the gate. Why not? Well, for 2 things. You can, and they would have to modify this here to add AZ monitoring instead of just monitoring. So I thought it was easier to just have this here as a service monitor, and now you have full control of exactly what is happening there. I also have telemetry for the re-ranking and right here, the embedding NIM. And you can see we're filtering that out by a specific name. Again, if you are reusing this and your models are different, change this, tweak it, make it yours here, because this is really the idea behind this whole thing. So going back here, now you have an idea of how this works, which again does work from Cloud Shell directly. You can do it from there. And then one last thing I want to tell you. So once this is all done and you're cool with like, hey, I think this works out just fine. I do have instructions on how to tear it down. If you want it, it's all there too. But let's take to the next level. We know how this works, and we know potentially that there's a need here for scaling out. Now the question is, what metric are you looking at, and how are you scaling out? So I did mention the horizontal pod auto scaling, HPA, which is generally what we're going to be using for this, which is an excellent segue to this blog post, and I'll put that here for everybody as well. So if you don't mind, to just drop that. So what do we go from here? We already have the cluster in place. We know the RAG blueprint and the AIQ web UI are working. We actually have done some research, right, on AKS. Where you can go from here now, because we have everything instrumented, is you can take it and then have so that you scale out components that are under pressure. This blog from NVIDIA is excellent on that. And what it does is it will walk you through, and I'll go real quick so you can kind of see it. It will walk you through a very similar approach to what I'm showing you right now. And it will create, let me show you here. It will create, here we go, a set of rules that the horizontal pod autoscaler can use to scale out a given NIM. In this case, the NIM LLM, right? And I actually have all of this script, including the GenAI perf, in the repo. You can run it, you can use it too, and you can see the autoscaling actually working. There are two approaches in here, and I'll wrap it up with that. One, you can use the Prometheus adapter, if you're familiar with that, install that in cluster, and then use that with the telemetry provided by Prometheus to do the scaling of in this case, of the NIM LLM. The other approach is this. Now that I have everything wired up, you can follow this pretty much to the letter with one difference. You can use KEDA, the Kubernetes event-driven autoscaler, to scale your cluster in and out as well. So Azure provides you that capability. I mean, KEDA is open source, and the CNCF. AKS actually has that as an add-on. You can just turn on as a flag, and you call it a day. So you can use KEDA, you do some wiring, and then you can achieve pretty much what we have here. Or you can just use the Prometheus adapter. So with this, I know there was a lot of things. I will leave us with the cool Mr. Robot-like dashboard. And thank you for the time.
Thank you all for joining, and thanks again to our speakers. This session is part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. And we'll see you at the next one.